zero. Right? So we call theorem number 5, I believe. Yeah. Right. So and T is a Poisson process. According to the definition one F and F, the following hold. Assuming T greater than S. And for 3, suppose you have a sequence of increasing time, so for T1 less than T2, okay. For T1 less than T2, the last less than Tn, I have 1. And so Tn minus n sub Tn minus 1, all the way down to n T2 minus n T1, and T1 are all independent. Okay. So I believe I completed the part 2. Or prove part 2 did that? Was just a application of the tau K prime above there. Okay. And so part 3 is pretty much similar, I would say. Pretty much similar. We just have to invoke that property about tau K prime above there. So what is this? So n Tn, right? So continue from 3. So let me sketch it out here. I have Tn minus 1. This is my Tn. This is the arrival T of n T and minus 1. And then starting from here, I have less guy. Sorry, this is plus 1. Further along. So this will be T and so Tn. Okay. So this is tau 1 prime, tau 2 prime. So we observe what I have a number of the guests inside of this interval running from Tn minus 1 up to Tn. This is the maximum, let's say maximum of K, where I have, this will be the maximum of K of the summation of tau I prime. I from let's say 1 to K, just that this is less than the number of guests inside of this interval, which is Tn minus 1. Alright. And so because these tau I prime here are independent of the past, right? So, and since the tau I prime, so starting from time, so after I would say, right? So after T and minus 1 are independent of the collection. What collection? So that will be n sub T n minus 1, n sub T n minus 2, that indicates or implies immediately that and Tn minus Tn minus 1 are independent of the previous collection, the collection from n t n minus 1 minus n t n minus 2 all the way down to n t2 minus n t1 and n t1. Frequent. Yeah, pretty handy here once you have that property from the tau k prime. Okay, so let me put that final remark here. So what is the final remark that I want to say is, so in general, whenever you have such a process satisfying property 2 and 3 for a general distribution over here, then this is called stationary increment, independent increment. So let me write that. In general, a process, let me give another name here. A process, let me call process Xn. All right. That's just that. The distribution of x t minus x I guess x t s depends on the difference between the time depends on this, not on the time, not on the times of t and s. So the distribution is determined basically by the length of the difference in time, not the times themselves like a t and s. All right. Second piece, the so-called independent increment, namely for any sequence of, let's say, t1 less than t2 not less than tn, we have x, so tn minus x, tn minus 1, tn minus 1 minus x, tn minus 2, all the way down to x of t2 minus x of t1, and x of t1. If they are all independent, right, then the process xt, then xt is called, sorry to say, is said to have stationary independent increment. Okay. The part 1 is the stationary of the increment. The part 2 is about the increments are independent. All right. In general. Okay, so maybe should have mentioned about the derivation of the Poisson process in the first place to help with the math here, because I realized that a lot of people already took a 170B. So let me move. Okay, so that is that. So now let me move on to part 2. It should have been part 1 right from the get-go, but I forgot the derivation. So the problem is following. Given guests, right? Again, given guests arriving at a bank, say, we like to assume the following. We assume the following. A. So I want to put I want to propose a simple model to model the arriving guest at a location. The first A is suppose I have for, let's say I have for A less than B less than C less than D. Guests arriving in the interval A, B, and C, D are independent. So sketch it out here, A, B, C, D, A, B, C, D. So guests over here, the guests over there, they are independent. So if I have a non-overlapping intervals, then the number of guests arriving in each interval are supposed to be independent. And that is one assumption. The second assumption is the following. Now for B, I'm assuming the following. Let's say for epsilon really tiny. This means very small compared to. All right. So for any epsilon really tiny, we have. So I should say there exists a lambda positive, just that for all epsilon very tiny, I have a probability of what? I have probability of what? At least two guests in the time interval t to t plus epsilon. This is 0. All right. What does that say? That says if I have really tiny time interval, I can never expect to have two guests arriving at the same time. All right. If I really take epsilon very tiny, so always one guy walking through a door before another guy. If I divide the length to very small. In part 2, probability of exactly one guest in this small time interval is approximately, let's say, proportional to epsilon. So lambda times epsilon. In other words, this is proportional to the interval length, I would say. To the interval length. All right. So it's just exactly one next here. And so as a consequence of this, probability of no guests in this time interval is simply 1 minus lambda. So now the question is, what is, so how do I say, so denote by, let's say denote by n sub 1. Again, this is the number of guests guests in the first hour, let's say. Okay, in the first hour, I want to know the distribution of anyone. So let's say the right distribution of anyone. Right? Okay. So now, what is the idea here? So of course, this is just a problem about trying to model the number of guests arriving in this first hour, and apparently we have to do some approximation. Right. We have to do some approximation. Okay. So the approach here is the following. So we're going to divide through the, so step one. So let's say we're going to divide the first hour into very tiny disjoint intervals with equal length. Let's say 1/n. So let's say this is a 1/n. Maybe 1/n here. 2/n. 3/n, right? But one is simply an okay. And so here, so now what can I say? So now the probability of N1 being K. All right. So what does that say? That says I have K guests in this first hour, and in terms of these intervals over here, that means I would say approximately. Should say approximately here. I have K guests arriving. So just say K. Should say intervals having one guest each among an interval. Okay, right? That means among these small sub-intervals here, I have K of them expecting one guest each, and the rest with no guest. And as you can see, this is just a binomial distribution. So this is binomial with the parameter n, and the p is simply lambda, I should say, what is probability here? Lambda times the epsilon, which is lambda times 1/n. Right? And that is recording by the binomial distribution. This is n choosing k. I have what? P, right? So p raised to the power of k, which is lambda over n raised to the power of k, and 1 minus lambda over n raised to the power n minus k. Right? So now step 2 is we're gonna take n to infinity with k and lambda are fixed. Right? So if I take if I take n to infinity, k and lambda being fixed,
It should be a normal.
it should be what?
A normal distribution.
A Poisson distribution actually. Alright, so actually this product over here will go to let me call this star here. Star actually will go to Poisson distribution, namely this is e to the minus lambda times 1 technically. Here I have lambda to the k over k factorial, right? Which is the Poisson distribution. Alright, so this is the mass function of Poisson distribution. And that's why we have the property of the Poisson process. Okay, you have like an independence increment and a distribution of each interval. The number of guests on each interval has a Poisson process. All right. So I guess we want to go to the conclusion. In other words, we are confident to say the probability of number of guests arriving in the first hour can be written as E minus lambda. So this is 1 minus 0, right? Times lambda 1 minus 0, obviously raised over k factorial, right? Which explains the idea of the Poisson process. Why we have the Poisson distribution in the first place. Right. Later on in chapter 3, you will see more generalized version of the Poisson process. Okay, but now, all right. So the last piece in this portion here is on about the small result limiting behavior of Poisson process. All right. So this is a theorem. Say something with probability 1. The following holds. That's the following holds. And d over t will go to lambda as t goes to infinity. Right? That's probability 1. So what is the left hand side here? The left hand side is basically the what do I say here? Like on average, right? On average, how many guests should I expect in 1 unit of time? Right? Number of guests in 1 unit of time. In the long run, will converge to this lambda, which is basically the meaning of the Poisson distribution, because lambda is somehow kind of be thought as the rate I would expect to have in 1 unit of time. So so proof here. So step 1. So step 1 is strong law of large number. Strong law of large number. Following. So observe that I have what? I have and so. So let's say and so. N minus 1 and 2 minus n1 and n1 minus 0. This is just 0, right? This collection here are I and E distributed as a Poisson distribution with the rate v lambda. so that by strong law of branch number, we have n sub n over n is written as, this is n sub n minus n minus 1 plus n minus 1 minus n sub n minus 2 all the way down to, sorry, so this is plus n2 minus n1 plus n1 minus n0 divided by n. This will converge, so I'll just say with probability 1, this will converge to expected value of n, so let's say n1 minus n0, which is the mean of the Poisson distribution. Right? So I should say that's n going to infinity. Okay. So now, so this will hold for integer time step. So how do I convert to any real time? Sorry, for any real time t. So now step 2, in order to include any real time t, I have to follow. So observe I have what? So let's say nt over t, right? Basically, I want to do a what? I want to bound this ratio from above and from below. So this is less than 1. So I'm sure you agree with me. This is less than integer part plus 1. Yeah. Divided by t. So we're going to do further. T plus 1 times integer t plus 1 divided by t. Okay. Yeah. Well, this is one of the first guys because what? Because if I have, say, s less than t, then the number of the guests inside this 0 to s is always less than the number of guests up to time t. Right? Yeah. And so similarly, what can I do from below? I'm going to take the integer part of t here. So this is n, number of guests up to the integer part of t divided by t. But of course, now I'm going to replace this by the integer of t, but then multiply it back. Divided by t. Okay. So, what can I say now? If I take t to infinity, apparently by step 1, so by step 1, this ratio here going to lambda. This is step 1. And this ratio obviously going to 1. Obviously. As t going to infinity. And similarly for the other side, this is going to lambda, again by virtue of step rule 1, and then this clearly going to so I'm being trapped between two sequences, both converging to lambda, so I have to go lambda. The conclusion here is nt over t must go to lambda. Right. And this has to occur with probability 1. So for sure, that ratio has to go to lambda. As of course t going to figure H. G. All right, so I finished this chapter 2, and now let me move on to the next section, chapter 2.3 on the compound Poisson process. So the motivating example here is the following. So I have, suppose I have, let's say, cars are riding according to a Poisson process. Alright. So now I will consider that for each car I have, say I have a number of guests. So let's say the I car has, let's say a number yi, number of guests, right? So think about it. We have time 0, time t1. This first car here contains y1 number of guests. At the time t2, the second car will contain, say, a y2 number of guests, so on. Fixed on t here, and say tn. Alright. So I have n cars total, and I have a sum of those yi being the total guests arriving before time t. So denote by, what do we want to say? So maybe t, so now t, right? So denote by m sub t to be the total guest. Total guests arriving before, let's say, before time t. According to the graph, that is basically y1 plus y2 plus y plus all the way to y sub and t. And of course, maybe allow me to write down this summation. So I from 1 up to t of y, right? So one question here is, on average, how many guests do I expect to receive up to time t? So the question is that really going to of course here I'm assuming collection of yi. Alright, the number of guests for each car is, they are IMD independent of NT. So in order to answer this example, I need to mention the first theorem, one which is theorem 2.8 in your textbook. The following: suppose I have a collection of yi being D and also independent of the following: a random variable n, a random variable taking values in 0, 1, 2, 3, so on. Right? And denote by S being the sum of the yi. So has 1 to n yi. Alright. Of course with the convention that mentioned that if the n being 0, then if n being 0 happens to be 0, S is identically 0. Okay. So note that here I am having a random sum. The capital N is a random variable, not a fixed number. So now the theorem says the following. Following hold are A. If I have a specific value of the absolute value of yi, alright, and the specific value of n, they go finite, then the specific value of S is simply product of them and time the specific value of y. This is pretty clear from a heuristical point of view, because if n were fixed, right? If n were fixed and constant, then expected value of S is just n times expected value of y. So if n is simply a constant, then expected value of S is simply n times expected value of y. Right. So that is the first part. Second piece is about the variance, provided the y, the n will have finite second moment. So if the second moment is finite, then the variance of S is following. So you would have the, what do I say here? So you would have to think about, that will be expected value of n times the variance of yi. Plus the second piece is when, what do I have here? So the second P is about the variance of n multiplied by expected value of yi squared. Okay. Which might be a little bit mysterious. Seems to be mysterious in the sense that it may be tough to memorize this, but actually it's not really that bad. That is the way I remember that variance formula is following. So you think about when one of them being constant, suppose, again, if n is a constant, if n is a constant, alright, then the variance of S is what? Variance of summation of yi times 1n. And because they are all independent, that is just the sum of the variance. Sum times 1n, variance of yi, which is n times variance of yi, which is the same as expected value of n times variance of y. Alright, so that is one piece. Now we'll explain the first term on the right hand side. Okay. So now on the other hand, suppose if now instead yi is simply a constant. A constant, then what did you get here? So you have variance of S, right? Is now if y is a constant, let's say a constant c, say, alright? Then I have basically variance of what else? So replace yi by the c, so that will be c times n, and that will be, according to the formula, you let you know this is c squared times the variance of n. And the c squared is basically expected value of yi squared, which is expected value of yi squared multiplied with variance of n. Alright, so that will give you the second term on the right hand side. Okay. And of course now, of course we have to pay attention to the cross term, if any, but the truth is no, we don't. So we only have the two pieces like this. Cross term will be gone. Alright. So the proof, for the proof of the theorem over here, I will just refer to the textbook, because it's not really difficult, or not really anyway. See textbook. Okay. I guess just let me. I still have one piece around the compound process MT over here. But maybe for the sake of completeness. So let me come back to this. So let me come back to this for the sake of completeness. So now, so here returning back to the motivating example. So the motivating example. So the total of the guests that I would expect to have before time t is simply what expected value of nt, my Poisson process, times expected value of the number of guests for each car. Right? And recalling this is simply lambda t. Expected value of y. Alright? And note that MT is called a compound Poisson process. Okay. Right? It's not a Poisson process. MT is not. But it comes from a Poisson process. Alright, so in general, MT is not a Poisson process itself.